Hi everyone, this is Matt Ingram again with Replication 3A now. We're replicating the 2013 piece by Steve Messner et al. And in this particular video we'll be doing the replication in GeoDa, but we'll also be conducting the replication in R and Python. Here's an overview of replication 3 again of this piece in Justice Quarterly in 2013. We will be using GeoDa R and Python. Messner et al. Examined both robbery rates and assault rates, but in this replication video I will only be focusing on the robbery rates. The tools and techniques are the same for the analysis of assault rates. So we'll go over all of the tools and techniques for examining robbery rates, and then we'll leave the analysis of assault rates up to you individually. Also, the replication will focus on using 15 nearest neighbors, a spatial weights matrix constructed from the 15 nearest neighbors. Messner et al. Say that they do some sensitivity or robustness checks with 13 nearest neighbors and 17 nearest neighbors. We won't do all of those robustness checks or sensitivity analyses here in this replication video. Again, I leave those auxiliary analyses up to you individually. So as a last set of preliminaries, as with previous replications, I assume that you have downloaded and installed GeoDa, and by now you should be very familiar with the GeoDa environment. I also assume that you've downloaded all of the data and replication files from our classroom site and have all of this material accessible in a single folder which you're considering your working directory. So let's go to GeoDa and the article and get started. So this is the article that we are replicating. Just to confirm that we're doing the same article, I expect that you've read the full article. There is substantial theoretical motivation discussed in the front part of the paper. Also some material providing some context on Germany and criminological research in Germany. There's a really good overview of comparative literature on crime and the spatial analysis of crime. But we're going to be focusing on the results sections, which begins on page 1027. So here we are on page 1027, and as the authors state here, at the start of the results section, the empirical analysis begins by examining some percentile maps. So let's go and start generating these results here. So if we open GeoDa and bring up our shapefile, let's go to our replication folder. This is the shapefile that contains all of the data. So we see, as with previous replications, the GeoDa generates this themeless map just to confirm that we're working with the correct geography. And if we open up the table, we can see all of the values here. It looks like the ID variable is this new ID 2, although it has some decimal. It's maybe the precision of this variable is higher than is necessary, but this looks like the ID variable, and then the rest of our variables are in this table. So if we wanted to generate some percentile maps, well, let's go to the replication assignment and do things in order here. Here's the replication assignment that corresponds with the article, and what I've done with this replication assignment, it's not entirely clear in the article what variable labels correspond with what variables, so I've just outlined them here briefly. You see the two dependent variables, and then all of the independent variables, including some regional dummies and then some interactions at the end. So these are all the replication items then that we're going to be working through. I was just about to start with these percentile maps. So let's do the items in the order in which they appear here on the replication table. So let's first construct the spatial weights matrix. So if we go back to GeoDa, we have our data loaded, and now we can go to Tools, Weights, Create, and this is where we would create our spatial weights matrix. If we pull down the ID variable, you can see that it's not giving us the option of selecting new ID2, so let's just add a new ID variable. The default name in GeoDa is polyID, but we can make that equal to the new ID2 variable, and this should create a new ID variable called polyID. If we go down to K nearest neighbors, this is where we would create our nearest neighbors weights matrix, and let's just increase this number 4 to 15, and we can create it. Here we are. I've already created it before, so I'm just going to replace it so we can get that done. Success. So our 15 nearest neighbors spatial weights matrix has been created in GeoDa. If you recall from the paper, they say that they create a symmetric weights matrix in R, which they then presumably loaded into GeoDa. We'll just work through to GeoDa to see what happens, and then make corrections if necessary. Before moving forward at this point, you could create your two other weights matrices, the 13 nearest neighbors and the 17 nearest neighbors, if you just wanted to see what happens with those weights matrices. But for now, let's close. And now we've done this first step, so let's look at these percentile maps. Again, I will only do the first percentile map in figure 1, since the tools are essentially the same for figure 2. So what we're trying to do is replicate this figure here in the original published article. This is figure 1, the percentile map. If we set it off to the side and then bring GeoDa back up, if we go to Map, and Percentile Map is how we would create a percentile map, as we've done before with quantile maps or box maps. And then we want the robbery rates variable. We have two variables here, the raw robbery rates and logged robbery rates. We'll want to use the logged version of the variable in our regressions. But for now, let's use the raw rate. And so let's click on that and click OK. And this is our percentile map from GeoDa. Right away, you can see a good correspondence between the published map on the right and the map we've just generated on the left. Ours is a color map, but basically if you look at the legend, you can see that the smallest 50% of values are represented in blue. Those tend to be in the southern part of Germany, and the largest 50% of values are represented in red. Those tend to be in northern Germany. Indeed, the smallest values are in dark blue, and those cluster around southeastern Germany, and the very highest values appear in dark red, and those are sprinkled about in northern Germany. So just a cursory glance at this map shows a good correspondence, but if we wanted to make it reflect the published map more closely, we could change the colors in our GeoDa map. So let's make the smallest values light gray. We right click on that category. Let's just pick the third lightest gray, right click on the category, and again pick the third lightest gray. For the middle values, let's just make them white for clarity of presentation here. And then let's make our largest values a dark gray. So now we've got a map that looks very much, it's essentially the same map as the one in figure 1 in the publication. So again, just to remind you, you could right-click on this figure and copy and paste this image into another document, or save the image, export it, and import it into another document if you needed it. For presentations, you might want the color map, but for articles and other submissions, you might want to have both on hand just in case the journal does not do color figures. So let's minimize this and go back to our replication assignment. So we've constructed the spatial weights matrix. We've got our percentile maps underway. Now let's do item 3 here, the LISA cluster maps. Again, let's just do the LISA cluster map of robbery. That would be figure 3. So figure 3 looks like this. Here is figure 3. You see some high clusters, regions of high clusters in northern Germany, and then a large number of low clusters in southern Germany. So let's try to replicate this. In GeoDa, we would do that in space and go down to the 4th option. We've got our variable selected, and we've already constructed the spatial weights matrix, so it's got it loaded in as the default spatial weights matrix. And we could pick all 3 options here, the significance map, the cluster map, and the Moran scatter plot. But let's just keep the cluster map option here and click OK. And here is our LISA cluster map. We might want to increase the number of permutations to 1,000, say. And again, even a cursory glance at this map shows that it corresponds with the map that was published as figure 3 in 2013. Again, if you wanted to make the map look more like the published map, you could change all the colors. I won't go through those steps here, but you could basically change everything to white except for high and low. In high you would make dark gray, and low you would make light gray, and then the map would look essentially the same as figure 3. So let's return to the replication items. At this stage, you could go and fill in the percentile map for the assault rate and also reproduce the LISA cluster map for assault rates, but let's just keep our focus on robbery rates and continue with the OLS model and spatial diagnostics. I would draw your attention to the article and note that the OLS model and the diagnostics are not fully discussed in the paper. Here we are at the bottom of page 1028, and you can see that they're concluding their discussion of the exploratory spatial data analysis, the LISA clusters, and then this is the extent of their discussion of the OLS models and the spatial diagnostics. So they're telling us that they did run an OLS model and they did some diagnostics on it, and so they found that the residuals were clustering together in a statistically significant manner, and that the spatial dependence was best modeled by a spatial error process. We know from our own discussions and in class that they were probably using the Lagrange multiplier tests here to diagnose the spatial error process, but they don't specifically say that that's what happened. So we want to do run our own OLS model and conduct our own spatial diagnostics and see if that leads us to the same conclusion. So how would we do that in GeoDa? In GeoDa, the regression methods are, the regression tools are under methods. We can open up the window and here we can specify our model. Once again, you want to use the lagged version of the dependent variable, the lagged version of robbery rates, and slide that over into the dependent variable. And then if we look in the article, you can see in table 1 we essentially want to reproduce this first model here, model 1 in table 1. Note that model 1 is already a spatial regression, right? It has the lambda term here for the spatial error component included in the model. So this is not the OLS model, but if the OLS model, the basic OLS model would consist of all of the other predictors in model 1. So let's pull east into the column of independent variables, south, and then resource deprivation is RDEP1, urbanism is PORB1, divorce is here, and the age structure is here, and the sex ratio is here, and then the interaction term appears in the second model. So this is our complete model. Again, if you had any doubts about what these variables were, you could go back to the beginning of the replication assignment and you see the variables are described here. So again, let's pull up GeoDa. This is our dependent variable, our independent variables, and we can run the OLS model on its own here just by clicking run. This gives us the OLS model results. But I'm going to close this window because what we really want is the OLS model with the spatial diagnostics, and in order to do that we need to make sure we bring in the weights file. So now we've got our weights file connected to our OLS analysis, and this allows us to generate some spatial diagnostics. So again, we can hit run again. Here we see the same results, but at the bottom we see the spatial diagnostics. So if we look at this, it doesn't really make sense to examine the coefficients because we don't have anything to compare it to in the paper, since the original OLS model was not reported. If you wanted to, you could compare some of the magnitude or the statistical significance or the direction of these coefficients to the ones in this model. They are close, but again, these are not the same models. This is a spatial error model, and this is a simple OLS model. But in general, there's some rough correspondence there, so it looks like we're on the right track. One thing that jumps out here is this multicollinearity condition number. As a general rule of thumb, you want to be concerned about multicollinearity when the number is above 30, maybe even if it's above 15. That's a general rule of thumb. In either case, in any case, this number is much higher than even 30. So there's a strong indication that there's some multicollinearity going on in the model. But let's skip past that since that's not directly relevant to the published material. So here are spatial diagnostics, and here we see that when we're looking at the residuals of the OLS model, there's a substantial amount of spatial autocorrelation. It looks like the errors are clustering together in systematic ways. The Moran's I is about 0.25, and it's highly statistically significant. Again, if you wanted to compare that to the Moran's I reported by Messner et al., you could go to the bottom of page 1028. And the Moran's I that they report for robbery rates is 0.224. We've got 0.247. It's close. It's not clear why. They might have been using a different weights matrix. We're also not using the symmetric weights matrix that they said they use, so we'll get to that in just a second. But in general, it looks like we're still on the same track. As you note here, they said that the spatial dependence is best modeled by a spatial error process. Now, if you recall the flowchart that we discussed in class, what we want to do at this stage is to look at the basic LM tests, right? The basic Lagrange multiplier tests. So we want to look at the basic lag version of the test and the basic error version of the test. If both are significant, then we move to the robust ones. So let's look at these. This is the basic lag test. It's statistically significant, and the value is 46. The basic error test is also statistically significant, but it's much higher. So at least right now there's a preliminary suggestion that maybe the spatial error process better fits the data than a spatial lag process. Since they're both statistically significant, however, we can move to the robust version of the test, and here we see that the robust LM lag test is not statistically significant, while the robust LM error test remains highly statistically significant and is still very large. So this is our strongest indication that the spatial dependence, as noted by the authors, is best modeled by a spatial error process rather than a spatial lag process. So at this point we would want to specify some spatial error models, and that is exactly what the authors do in Table 1. So let's reproduce these models now. If we close this, we've got basically this model, and we just want to run this as a spatial error regression. So in GeoDa, it's as simple as clicking this dial button on the right, spatial error, and then running it. This is where we run into an error in GeoDa because the regression requires asymmetric weights, but the weights created by GeoDa were not symmetric. So this is where the authors say that they go to R to generate a symmetric set of spatial weights and then export those weights to as a GAL file, as a GAL file for use in GeoDa. I won't go too much into R now since we're going to do the entire replication in R anyway, but if we glance at the R code, this is the R code that should be familiar to us from previous replications for generating spatial weights matrices. And this is where we would how we would generate symmetric lists. We've done this before, again, for, say, Baller et al. and another piece by Steve Messner and his colleagues. But essentially what we've done, what I've done already is create a symmetric version of the 15 nearest neighbors shapefile, and I made it into and I exported it as a GAL file using this command, write nb gal. So it should be in our working directory as 15 nearest neighbors symmetric gal. Again, we'll come back to this when we do the replication in R. For now, let's go back to GeoDa and select a different set of weights. And we can see here is the symmetric version of the weights that I generated in R and then exported as a GAL file. Now we can import them into GeoDa. So let's open this. We're going to set that as the default. Yes. And now we've got our symmetric weights matrix here attached to our OLS model. So now we can run this as a spatial error model. Let's see if this runs now. It does indeed run. And here are the results that should match the results in Table 1 from Messner et al., at least for Model 1. So for the east, we've got a coefficient of a negative relationship, but it's not statistically significant. The magnitude of the coefficient is not matching. It's smaller in our results. But at least the direction and the statistical significance is the same. They found a negative non-significant relationship. We find a negative non-significant relationship. And everything else except, no, including divorce, everything else is statistically significant in their model. And everything else is statistically significant in our model. Then the south has a negative relationship. The south has a negative relationship. In our model, the resource deprivation has a positive. Actually, the next four variables, resource deprivation, urbanism, divorce, and age structure, all have positive relationships. In their model, all of those variables also have positive relationships. And then the last two, sex ratio, just sex ratio is the last one. It has a negative relationship. That also has a negative relationship in our model. And then lambda has a positive and statistically significant relationship, and we find also a positive and statistically significant relationship. So we've just replicated the results in model 1. Again, some of the coefficients, the magnitude is off slightly. I have some ideas about why that might be the case. We're using, again, a 15 nearest neighbor symmetric file. I did some digging around, and one of the nice things from this piece is that the authors shared a lot of their replication materials, and this is their output from GeoDa for model 2 in table 2, and you can see here that they're using what looks like a 13 nearest neighbors weights matrix, so that may explain some of the difference. So you could replicate this analysis by generating a 13 nearest neighbors symmetric weights file in R, exporting it as a gal file, and then running this analysis again, and hopefully the coefficients would line up a little bit more closely. Those are details, though. There are no meaningful differences really between the results that we just generated and the results that were reported in model 1. Let's run model 2 just to complete this. So the only thing that we're going to add here now, looking at the article, is this squared term for urbanism. That is this term here. Let's bring it over to the independent variables, and then we can run this model again. So this is model 2. We see the east is still, and the authors reported it as being non-significant. We also find the same thing. It's non-significant. Every other variable is significant except for divorce, which we find is non-significant, and which they also found did not have a statistically significant relationship with robbery rates. Beyond that, we could look at the direction of the coefficients. South is negative for us, south is negative for them. Resource deprivation is positive for us, positive for them. Urbanism is positive for us and positive for them. Age structure is positive for us and positive for them. And sex ratio is negative for us and negative for them. And then the urbanism squared term is negative for us and negative for them. Lastly, the lambda term is positive and highly statistically significant, and they find the same thing. So we've essentially reproduced their results. We could discuss a few finer points about this model, how to interpret the squared term. This interaction might be one interesting point. But in essence, we've just replicated the core empirical results from Messner et al. For robbery rates using only the 15 nearest neighbor spatial weights matrix, which is the main weights matrix that they said their results were based on. So now you could go back and replicate these results using either different weights matrices or the other dependent variable assault rates. I'll leave that up to you. Thank you.